So I have a little graphics program, statistics graphics program here, and it'll just be good to demonstrate a little bit of the histogram we were talking about last time. So you were here for the histogram, right? Yeah. So you remember what the area on the graph represents? The frequency. How many? So if you had like, I don't know, we'll do like a histogram of people's heights maybe or something like that. Okay, let me put in some data. Right, so we'll say, I don't know, what would be an average height? 160 centimeters or something? And then we've done standard deviation, so we'll say later. We'll say standard deviation of 5. And we'll say our data will have okay, there we go. Whoops, maybe that's too many. I think that's a bit too many. Okay, so what I've just... Rats. How do I clear this? There we go. So what I have here is... Oh, no, that's not good. Height can't be negative. Let's try this again. I'm trying to generate 100 random heights. I have it backwards, how I typed it in. There we go. Okay, so here's 100 random heights of people, and we can put this in a histogram. So you'll look and you'll see, you'll get your histogram, and it'll pop up on the side here. Come on. There we go. There we go. So this is the histogram of 100 people's heights. Come on. If I make this one larger, maybe like 1,000 people, and draw the histogram. I get this shape. If I make it, let's say, 10,000 people's height, I get this shape. So how would you describe what's happening to the histogram as I have more and more people added to my data? So let's say 100,000 now. 100,000, and let's draw the histogram one more time. That's it there. That doesn't look much different to me. What would you describe as happening to the histogram? It looks like it's getting smaller, but describe more the shape of it. What shape it makes. So maybe we need to go back maybe to the first one, for example, when I had 10. So this is the shape when I had 10. And now let's go 100,000. It's the shape of 100,000. So what's the difference between the two, would you say? They're both rectangles, but look at the overall shape. What's happening here as we have more and more data, the shape is becoming more and more like a curve, like almost like a concave quadratic. Let's add in 1,000,000. I hope this doesn't crash it. We're good. And graphing. This is 1,000,000. So as you can see, the more and more data we have in, the more we have this kind of curve shape to it. So this type of histogram is called a bell curve, which maybe that's a term you've heard before. So it's just good for your vocabulary, and we'll need this for this chapter and the exam. Shapes like this are called bell curves. So maybe that's the first thing to write down, is just the name of the shape. So if you can just try your best to draw a shape like this. It's a bit like a quadratic, but one difference between this and the quadratic is when we come down at the bottom here, you know that the quadratic crosses the axis here, whereas this graph kind of curves and flattens out at the axis. Can you see that?
Yeah.
Kind of flattens off, whereas the quadratic would curve down. I'll draw it here too. Called a bell curve. Okay, you got that? Yeah. So, this leads us into our next idea. We have this important variable, which often is called z, and we say z equals n0, 1. Squared here. This part here is the mean, and this part here is the standard deviation, sigma. And the reason z is so important is because when we plot this z, it has three important features. Number one, we'll say the histogram of z is a bell curve. The mean of z is 0, and the standard deviation of z is 1. And I'll show you this now in a graph. You got that? Yeah? Okay, so this is what z looks like. I'll make 10 values. So here's example of 10 values for z. So z is a special random variable. What you notice about it, if I was to calculate it, here's my 10 variables. If I was to get 10 values, if I was to get the average of these, I should roughly get 0. And I do. It's not exactly 0 because it's random. And if I calculate the standard deviation, I should roughly get about 1. Again, it's not exactly 1 because it's random. And if I plot the histogram for it, I should get roughly a bell curve. Not perfect here because it's only 10. But if I jump that up to say 1,000, again, if I get the average, now it's closer to 0. If I get the standard deviation, it's closer to 1. and if I plot the histogram, I get something that's closer to a bell curve with the center at 0 and standard deviation of 1 then. This is an important variable in statistics, and for the rest of the chapter it's going to build upon this. Just before we go more into this, last time we were doing the histogram, and I asked Iyad this, and I don't know if you remember, Adnan. Do you remember what the area represents on the histogram?
The number.
Yeah, what's the word for that? The number of the things. Yes, frequency is called the area. So for example, if you had 100 data points, what's the total area here? It'd be 100. Yeah. What we're going to have a look at now is something called a density plot. And a density plot is just a histogram. I know it's not writing right now. Where the area is equal to 1. We'll load in a second. So what you do is you take your histogram and you divide all the heights by 100 in this case because we have 100 points. And what that does is it changes the total area to 1 instead of 100. Because it's like you shrunk everything by 100. That means that the area, instead of representing frequency, represents probability because the total is 1. So previously, if I said how many people are between here and here, then you would have to get the area. But now if I said what's the probability of getting something, say, from here to here, if you divide by the total frequency, the area now becomes a probability. So to make the plot, all you do is you take the histogram and divide by the total frequency. Yeah? Yeah. Yeah? Okay. If you could, I know it's not possible, but if you could make n equal to infinity, that means you have infinite points, and you try to plot your z variable, this special variable that has an average of 0 and a standard deviation of 1, you get this perfectly smooth bell curve. It centers at 0 and its standard deviation is 1. Now when we were talking about standard deviation, you might remember that we saw that roughly 2 standard deviations equals the width of the data. So this is about 2 to the left and 2 to the right. But of course we said it's 1, the standard deviation. So this is roughly around about -1, and here this is about 1. And if I asked you a question like, okay, how many of my z values will be between, let's say, 0 and 0.1, then what you'd do is you'd have to draw the density plot and get the area here. And that would be, for example, the probability z is between 0 and 0.1. And just to double check, what's the total area here? What's the total here? If this is a density plot, what would you say? Total area? Total area, if you remember, is 1, because I said it's a probability. Yeah? So, in the density plot, the total area is always 1, which kind of makes sense because the probability that z is between minus infinity and infinity is guaranteed. It has to be 1. So the total area has to be 1 here. If you look at the graph, what would you say the probability that z is between 0 and infinity? That z is between 0 and infinity. If that's this part of the graph, what would you say the answer is? No? A half, yeah. This graph is symmetric. It's the same on the left and the right then. Now, to continue, we need to practice calculating areas. So the good thing is, this graph is so important that there's already been a table made for it where we can look up areas on it. So we need to open the formula book, and I need to show you how to read that graph. So the next thing for you to do is open up the formula book on Moodle then. And I'll just close this graphing program. Well, this is very unusual. What happened to you?
I thought we were gonna start at 9:30.
Why would you think that?
I thought they would be right.
You guessed wrongly.
Yeah.
Okay. Have you got the formula book open? You getting it? No, Musharif.
That's so unusual.
No. Hey, Musharif.
No.
No.
Okay, we'll close it.
No.
Why?
Because this is your punishment for being so late. Sit down. You can close it in the second class. I wouldn't sit over there. The fan's on. Oh no, you're welcome. No need to thank me. I thought you might be a bit hot this morning because it's so sunny. Yeah. I said I'd better get the room nice and cold for Musharif because I don't want him too hot when he arrives. Yeah. Got the formula book open? Yeah. Okay. Right. Now, right. So, if you look towards the back of the formula book, and I think I might actually have the formula book as well if I open it too. If you look towards the back of the formula book, there should be a table that looks like a bell curve at the top. Now, if it's not on the top, it should just look like a big table with lots of numbers in it. It's usually the last page in the book. Let me see, what do I want here? Resources, syllabus and formula books. And I'm looking for the engineering formula book. Here we go. I'll explain how to read these tables here. Be strong. You've got a jacket, a sweater, shirt, and a t-shirt. You got 4 layers? 3 layers. Oh, well, okay. You only have 3 layers.
You have two.
No, I actually have 3. Alright, this is the normal distribution table. So let me explain how these work. We have this function and the way to describe this function, it's the area from 0 to z. So for example, there's 0. If I write this, it means the area from, not 0, minus infinity. It's the area from minus infinity up to the point 0. So this one here, we said would be 0.5. If I wrote this, infinity, then that would be this one here. The area from minus infinity all the way up to infinity. That's going to be 1. But if I wrote something like this, 0.1, what would that be? That would be the area from minus infinity up to 0.1, which would be there. So you realize if I said something like, what's the probability or the area between 0 and 0.1, and I'm only allowed to look up from minus infinity to that number. If I wanted this in-between piece, any ideas on what I would calculate? Yeah. Sorry, I didn't actually tell you the name of this yet. Does anyone know the name of this Greek letter? It's called phi. So phi 0.1 minus phi 0. Yeah. So it's like you're saying this area minus this area gives us the piece that I want here. This is what's in the table. So for example here, when you look up 0.1, that number there is the value of phi. Now you might be wondering, what's all these other numbers here? Well, this is 0.10, this is 0.11, this is 0.12. If you want to be more accurate. So the most we can do is 2 decimal places. This is the first decimal place and this is the second. So let's look up a value together as an example. Let's say phi 0.25. That would be the area up until 0.25. So if we look at the table, we go down to 0.2 and then across to 5. And the answer is 0.5987 as an example. So this is practicing reading the table. Another name for this function is called CDF, cumulative distribution function, whereas the previous one we did was density distribution or probability distribution. You know the word cumulative? It means like total. So it's like total up until some point. Okay, so this is practice in reading the tables here. You might want to write this down. And we did this one as an example. Yeah. Have you done this before? No. Come on guys, stick to English now. You better be asking them, what did I miss in the last half an hour? Yeah, really? Did you get a good answer?
Yeah.
So what's happened to Mayor now? Has he fallen off the face of the earth or what? I haven't seen him. The last time I saw him, that Thursday class, and the time before that, the Thursday before that, I think. Was he in on Friday? No, I had you on Friday, didn't I?
Yes.
Yeah, I didn't see him. Did I? No, I didn't see him on Friday. No. Yeah. Okay, do you have this? Now. No, not yet. This seems important. I better answer it. One moment. Hello? Stupid spam call. Right, did you write that down now? Yes? Okay. One problem with this table, if you notice, you can't look up negative values. You see the smallest value on it is 0. Do you see that? It starts at 0. So for example, if you wanted something like, say, this, minus 0.3, this area, well, we have a big problem because we can't look up minus 0.3. But this graph, remember, is symmetric. So I'll just give you 1 minute to think. How could I find this area using only positive values in the tables? And my hint is this graph is symmetric. It's the same on the left and the right.
So the same value of this one?
Not quite. See if you can write something down there. No, you're looking like...
0.7.
Yes, you're thinking along the right lines, but not 0.7, because remember, 0.3 is this point, not this area. Well, what you would love to look up is this, but you can't look it up, right?
Yeah.
Now, if you were to look up the positive version of it, you would get this area here, which of course is way too big, it's not what you want. But actually, if you think about it, this is the same as this here, which is at 0.3. And remember, the total area is 1, so this piece here will be 1 minus that answer. So your 0.7 had the right idea, but not the right formula here. So in other words, we can have this rather convenient result, that if you ever need to look up a negative value, it's just 1 minus looking up the positive value. So this is why there are no negative values in the table, because we can just look them up by making use of this property. So please note this rule or property. Got that? Can I scroll down a bit? Sharif?
Mm-hmm.
Yeah? Okay. So let's practice the looking up some values. So I'll give us 4 examples here to start with. 1, 2, 3, 4. So the first one, and let me just mark off 0 on each of these. So this can be 0.2. And this can be minus 0.1. And this one can be minus 0.1 and 0.1. And then this one here can be minus 0.3. And this one here, just to be clear, it stops here at 0.1 and minus 0.1 here, so it stops there. Okay, so here's 4 examples. I'll do the answers in 1 minute. I just want you to practice using the table book here to get these 4 areas. Do you have the formula book open, or do you need me to open it? Which one are you on yet? 3, yep. Oh no, please, English, please. Okay. We've got this. Well, Sharif, which one are you on? Oh my goodness.
What is the name of it?
Probably called like normal, standard normal. It's after the histogram one.
So finish it that.
Well, kinda. This is probability, but it just continues on from it. Yes, statistics are finished, but this is just the next part of it. Think you got them? Let's see. So the first one will just be table value of 0.2, which equals, if I go to my book here, you have it there, it's gone a bit slow here, it's stuck. 0.2 is 0.5793. Okay. 0.5793. Did you get that? Yeah. Okay, this is the table book value of minus 0.1, which is 1 minus the table book value of 0.1, which is 1 minus 0.5398. What's that? That's a 0.712? No, 612? I don't have a calculator. Oh, sorry. I'll have to do it the old-fashioned way.
Yeah,
0.4602. Great, thank you. Okay, this one here, it's the table book value of 0.1 minus the table book value of minus 0.1, because it's this area to the left minus this area to the left. But if we use our trick from earlier, this is 1 minus table book value of 0.1. So you can see that, let me see, that minus that is 2 of them. So it'd be twice the table book value of 0.1 minus 1 is what you would get. So if we look up 0.1, it was 0.5398. So it's twice 0.5398 minus 1. What's that, please? 0.1586. And this last one's a little bit tricky because this one here you're looking at the area to the right, which would be 1 minus the area to the left, because remember the total is 1. So it's the total area minus this area to the left. But if we use our rule from earlier, this is 1 minus 0.3. The ones will cancel and actually will be the same thing as table book value of 0.3, which equals 0.6179. So let's just write down what those results mean if we were to interpret them. So result 1, 2, 3 and 4. So result 1 means that 57.93% of Z values are less than 0.2. Result 2 means that, what did I get there? 46.02% of Z values are less than minus 0.1. Result 3 means that 15.86% of Z values are between plus and minus 0.1. And the last one says that 61.79% of Z values are more than minus 0.3. Now the reason you need to know that is because the question could ask you what percent of Z values are less than 0.2. So you need to draw that as the graph and get the area. I was saying to Musharif the name of this, another name for these Z values are, I wrote this earlier but I don't think I said it out loud, normal 0, 1 values, which is longer to say. And then another name for it are standard standard normal as well, or as I just call them, Z values, or sometimes people call them Z scores, which are slightly different, but that's okay too. So just different names for the same thing. Okay, can you write that down? Sorry, there got my shoe. Yeah? You got all this? Yeah? Okay. Let's just have a look here at the questions you have. So this chapter we're doing right now, this final chapter, it's new to the engineering syllabus. It's only been on it for like 1 year. So that makes me think like it's kind of highly likely that it's in the exam, because usually for new topics, they like to ask them, because then what's the point of introducing it if you're not going to ask it, So there's a good chance this will be on your exam, and in the last exam it was on it, and it was in section A. So it could be an A or B, so you can't avoid doing this one. Okay, let's have a look here. Yes, go ahead, Joe. Yeah, actually, you know what? Before we start these, if you want, you can take a break for a few minutes and then we'll start them, okay?